All right, very good. Welcome back, everyone, to another edition of Symmetry in Newcastle. It's been a while. We've got two speakers today, Roman Gorazd and then later Matthias Chen. We'll start with Roman, currently unaffiliated, talking about a constructive solution to the isomorphism problem of Higman-Thompson groups using gluing diagrams. Thanks, Roman.
Thank you very much. Thank you very much for inviting me or letting me invite myself, I guess. And it's good to be back in Newcastle, even if it's just virtually. So I'll be talking about the isomorphism problem of Higman-Thompson groups. And first, a little bit of background. Oh, there we go. Okay. Um, the Higman-Thompson groups were introduced by Graham Higman as a generalization of Thompson V, and they're very important examples of finitely presented, well, simple or almost simple groups. Um, he proved that if two of them are isomorphism, uh, well, they depend on two parameters n and r, and the first parameters have to be equal, and the second parameters have to do this GCD condition. And unfortunately, he was not able to prove the converse, but he conjectured that. And that was open for a good time, over 30 years. And in 2010, Enrique Pardo proved the converse implication using results from Levitt path algebras. And I've uh, I would struggle at least to get an explicit way to construct a direct isomorphism of Higman-Thompson groups from that paper. I don't think there's an explicit way there. So what I want to do is I want to give an explicit solution. I've talked to Matthew Brin about this, and he told me, well, the current methods work, but it's not sure why they should work. So I want to show why this isomorphism should be true. So I will introduce the tool of gluing diagrams, and the nice thing about gluing diagrams is there are a lot of pictures that I can use. So most of my presentation will just be pictures. Um, and then I will be able to use those fluid diagrams to follow the Euclidean algorithm to construct these isomorphisms. So first, I gotta do what I always do during these talks. I gotta define what a graph is. So a graph for me is just vertices, edges, and then an origin function and a terminus function. So it can have loops, it can have multiple edges, it is a directed graph. And if we have a graph, we also have the space of paths, which is just sequences of edges where the terminus and the origin are equal. And I also add the epsilon v's to be the empty path. So if we imagine a path being a journey through the graph, the empty path is just staying at the same place, not moving. Not very interesting, but it's convenient for the notation. And of course, if I have a path, we can define the origin function, we can define the terminus function in a standard way, just the origin of the first edge and the terminus of the last edge, respectively. Then, of course, the origin and the terminus of the empty paths will be just the vertices they are based at. And then we have the prefix order with, again, the empty paths need to be treated a bit differently. Just looking that the empty path is a prefix if and only if the origin is of the path is V. And well, we will say that they're independent if they're not prefixes of each other. Okay. This is still a lot of definitions at first. So we will generalize those notions to sets of paths. So we will say that they're independent, well, a set is independent if all the paths are pairwise independent of each other. A path lies under a set of paths lies under another set of paths if every Q in N, so every path in N, has a prefix in N. So you can it makes sense if you visualize the path space as a tree hanging off downwards. We will say that it exactly covers if N exactly covers M if N lies under M. And for every path that lies under M, so that has a prefix in M, there is a path that lies under N, i.e. has a prefix in N, such that P is a prefix of Q. So it's kind of, if we have N here, so let's say M here and N here, and kind of, there is no way out. So we can't go like this, for example. So it kind of covers it completely. And we will write the suffix M to denote every path that lies under M. So this way we can define the rooted path space to be all the paths with origin V. And we will call a subset of this path space a basis if it covers the empty set. So the empty set would be our root canonically. Okay, so now I can show some pictures, and let's look at a visual representation of this path space. So if we have a graph here, let's say it's two vertices, and we've got some loops, we've got double loops, and we can draw the path space to be a tree where, for example, this edge or this vertex would be just a path going once along the loop, and then this vertex would be going once along the red loop and once to the blue one, and so on. And for example, this vertex would be the empty path. But what's interesting here is we can kind of construct this tree from two different blocks. So we've got the block that's rooted at the square, and we've got the block that's rooted at the circle, right? And we start from a square, so we glue the block that's rooted at a square to the square, right? And then we keep gluing. We glue square to square and circle to circle. So we glue it two squares now and one circle, and then we go on and on and on and on. And in infinity, we will construct the whole tree or the whole path space like this. But those are kind of the basic building blocks. There are kind of non-standard ways of constructing this tree. So let's take this building block, right? So the numbers why they are there will get will be clear in a moment. So our this is our building block, and this is our starting starting base or starting kind of platform that we will build on. And we can glue this building block to this space by just saying, okay, 1 goes to 1, 2 goes to 2, 3 goes to 3. And here, when we glue 1 and 3, that's pretty obvious, right? The neighbors of 3 get the numbers that they have. Here, when we glue 2, nothing really happens except for 2 becomes 1. So this is kind of gluing an empty path. And now we have two partitions here, and we can glue again our building block to both of them, right? And we go again 1 to 1, 2 to 2, 3 to 3, and we get first this one, then this one, and we continue on, and we get the whole tree. So this is kind of, it shows, oh, we can construct a tree in different ways. And if we kind of squint at this block, if we ignore all the numbers, ignore how many vertices there are, if we just say, okay, this is a block that we can glue 2 copies of itself to, then it looks like this one, right? And this is the basic block of just the graph consisting of 2 loops. So there is a relation here, right, between this graph and this graph. And this thing is a gluing diagram, and this relation will be an isomorphism of the shift pseudogroup, but I'm getting ahead of myself because I haven't defined any of those yet. So to talk about gluing diagrams, we will first have to define gluing. Unfortunately, we will have to talk about multisets. I say unfortunately because multisets are conceptually easy to grasp, but they're sometimes awkward to notationally awkward. So what I do is I write gluing diagrams bolded, and the and elements of gluing, not gluing diagrams, sorry, multisets I write bolded, and the elements of them I also write bolded, and the underlying vertex or the underlying element I write unbolded here, right? So for example, if this multiset M would be circle, square, square, right? We would have here 1 copy of this tree rooted at the circle, and 2 copies of this tree rooted at the square, right? This joint. And we kind of want this to be kind of a few copies of the same tree. And yeah, we can write any element of this bunch of trees as a path in some rooted path space, and we have to specify which element of the multiset it is rooted on. So we put it as a subscript here. And this specifies the component it is in. And we can treat this basically the same way as we did path spaces. So we have prefixes, and with prefixes we can define being independent, exact covering, and bases. In this case, bases will be sets that exactly cover epsilon v. And now I just want to do a little remark. All the graphs I'm talking here are finite. Maybe it will work for some infinite graphs, but let's just, for the sake of this talk, consider them finite. Sorry. And now, if we have an independent set of paths, and we have a function, let's say we have a function from an independent set of paths to some multiset that respects respects the terminus, so the underlying vertices are the same. We can expand it to going from every path that lies under C to this multi set of paths here rooted at M. So here I'll define it formally as just setting, P, if we extend it by R, we get R rooted at the image of P, right? So here we can view it as, let's say this square goes to this square here, so this will be M, and then this R would go to this R. And if it's a bijection, if phi is a bijection, then its expansion to all of these paths is also a bijection. So using this, we can define gluing. So if we have a bunch of paths in this multi-path space, we can glue it to C by just taking the inverse image, right? So if we have something here, and then we have just one path here, can just take it back and glue it onto the square. Yeah, so this is very practical because we can kind of keep gluing, we can glue something to this, and if we have a function from D to the multiset again, we can keep gluing, and this way we do the kind of tiling building thing we did before. So now we can define gluing diagrams. Gluing diagrams will be, we'll have a few components. So first we have a multiset for every vertex in G, a multiset of vertices in H. So we're connecting a graph G to graph H. They're rooted, so we have a special vertex here, R and S, that's usually a root, but it doesn't even have to be a root in the end. We need a starting basis. So this was our kind of starting platform that we start gluing everything onto. And we get a bijection from the starting basis to the multiset of our root here, because kind of the empty path rooted on S will be kind of the starting point of H. And again, we want them to be terminus maintaining. So the underlying vertex of each image is the terminus of the path. So we can glue. And we want for every edge, a set of paths together again with a terminus maintaining bijection, such that they are disjoint. So they are disjoint, they're independent, and its union is a basis. So being independent is implied kind of by this. And yeah, so this will be a gluing diagram. A floating gluing diagram will be the same thing, just we don't have the starting basis. So we kind of don't have a basis to glue everything on, but it kind of floats in midair. So if we have the gluing diagram, as we did back here, we can associate with every path in, let's say this will be G, this will be H, and I'm using this and this as my roots. So we will associate every path in the rooted path space to a set of paths, an independent set of paths in the path space of H. And how we will do this is we will start with the basis. So we will start with, this will be C epsilon R. And we see, oh, this is the empty set based on our root. And the set not the empty set, the empty path based on the root. And the set of paths we associate with it is those three paths. And then we glue. And we see the set of paths associated with the green vertex is the green set, and the set of paths associated with the red is the red set. And we do this again. We see, oh, cyan is cyan, blue is blue, purple is purple, orange is orange. And we see, oh, so for example, the union of all those paths here is a basis, and the union of all those sets of paths is also a basis. And they're all independent, and they all have functions going to MV, or MR in this case. So formally, we can inductively define an independent set, CP, and maintaining bijection from CP to M terminus of P by just gluing on CE as we go along and composing with gamma E. Here again, we look at gamma Q to be a function to expand it on the path space. So this does make sense. And then we can show that if the paths are prefixes of each other, the independent sets lie under each other. If they are independent, the sets are also independent. And I think, well, the converse holds, except for the special case where the sets are empty, which can happen. It's not a very interesting gluing diagram then, but it can happen. Although it might be interesting. And this is pretty important. For any basis, the union of the sets of CP are also a basis, in this case, in the path space of HS. Okay, so now we've talked about gluing diagrams, and now we'll have to talk about shifts. So gluing diagrams will end up defining an isomorphism, well, not a homomorphism, if there are nice and isomorphisms of shifts. So we define shifts, and you can define shifts in a lot of ways. You can talk about shift groupoids and and Levitt path algebras, but I will keep it simple and define shifts as just functions. Well, shift representatives are functions from two independent sets that are terminus maintaining again. So the terminus is the same. And we can expand each independent set by gluing on a caret. Formally doing it like this. Of course, we are assuming that the path that we're expanding on is not a sink. If it's a sink, then we leave it alone. We don't touch sinks. And if we do this expansion, we can also expand a shift representative by any path R by just keeping it the same away from R, and then doing kind of the obvious thing, right? If we have a path that's mapped by pi to another path, we just map the edges to the edges. And we can do this because the terminus of pi r and r are the same. So this gives us an equivalence relation where the smallest equivalence relation where the expansion and the underlying representatives are the same. And this way we define the shift pseudogroup to be those elements modulo this equivalence relation. And the product is defined whenever we have shifts that agree with each other. Kind of had the same, well, the domain is the image, and then we just do the composition. And I'm calling it a shift pseudogroup to differentiate it from the shift groupoid, which is something else, which Matui and Matsumoto defined. It's not clear from this definition why it is a pseudogroup, but if we look at its action on the boundary of this path space, then we can see that it's a pseudogroup on the path space. And I think this was first, or where I saw it first was in Arklint's and company, don't know all the names, paper pretty recently, but it's a relatively straightforward construction, so I'm guessing it cropped up before that. So let's look at an example of a shift here. So here again we map red to red, green to green, and we kind of see, oh, this is not a basis, but this is a basis. So we can, it's not the full group. It's just we can map non-bases to each other. And if we look at, okay, we had this gluing diagram, and it gave us for every path a set of paths, and this set of paths will be endowed with kind of a numbering that we interpret as a function to the multiset. I can see, oh, if we have those sets of paths, we can map them to each other, right? We can take the red set, map it to the red set, and just say, oh, 1 goes to 1, 2 goes to 2, 3 goes to 3. And again, with the green set, we map 1 to 1, 2 to 2, 3 to 3. And that's another shift. So this way, if we have a shift or a shift representative in G, we also get a shift representative in H. So that's pretty nice. And it turns out, well, this is kind of the formal definition of what we did, right? So we take a pi going from two independent sets, and then we take the union of the CPs and we map them to each other using this, which when I was talking is just 1 to 1, 2 to 2, but it's basically going to the multiset MTP, which is equal to the multiset associated with pi p, and then going back. T. No, this is. So it's basically just going as here, going here 1 to 1, 2 to 2, 3 to 3, just written down so it makes sense notationally. And what's important is that if the representatives are equivalent, then their images are also equivalent, right? So we get an homomorphism of the pseudogroups of GR and HS. So I will show this just by kind of looking at pictures. The proof is not that hard, but you have to go through the gluing diagrams and show some lemmas, and it's early in the morning, so I won't go through all of this. So we have this shift that we were looking at, and we can expand it like this, right? And this gives us another shift or another shift representative, but they represent the same shift, right? So the shift representative associated in H to this shift representative is this, right? So again, we can see how it works. And the shift representative that's associated to our original shift was this, right? So we have to show that this thing is the same or equivalent to this shift. So to show this, we will just expand at 1 and expand at 3, and we'll basically get what we need. So if we expand at 1, I will just say 1A, 1B, 1C goes to 1A, 1B, 1C, and we expand to 3. Oh, it should be 3B. But it makes sense because it's a circle, so it needs to go to the circle as well. So if we have this shift, we can see this shift representative, we can see this is basically the same as this shift representative, just with different numbers, but that's okay. So morally, the reason why this proposition holds is basically gluing on additional blocks from the gluing diagram is the same as doing some smart expansions. So it doesn't really matter which representative we look at. All right. Now, since we have this homomorphism, we can ask ourselves, oh, when is it an isomorphism? So to see when the induced homomorphism is injective, there's a very simple method. We just check if the multisets are empty or not. If they're not all non-empty, the induced homomorphism is injective. It's not very clear from the way how I introduced it right now, but it gets pretty clear if you look at the path monad. So I won't be doing this proof. You'll just have to trust me that, or read the paper. It's going to be out soon. That this is true, and it's clear that if the multisets are empty, some of the multisets are empty, then it must be non-injective, because whether we take this vertex or not, it doesn't make a difference. So looking at the surjectivity, it's a bit more annoying because there is, we'll have to show that every shift kind of can be represented as an image of another shift, which is difficult. But the first step for checking it is checking if it's unblocked. So being unblocked means if we have some path in our path space H, then we can always find a CP that that lies under, or that has an element that lies underneath it, right? So we can kind of, the way we can look at it is this means that that all those blocks, when we glue them together, they completely cover our tree. There's no blockage that doesn't let us get to a certain path. So that's why we call it unblocked. And then we can look at the gluing diagram and determine when the basic shifts are in the image of the homomorphism. So the basic shifts are just the shifts with the very simple representative P goes to Q for any P and Q that have the same terminus. And we can check this by a very finite algorithm, or by a finite way of checking every internal path of the associated basis. What's an internal path? I will show you. But first, I will talk about unblocked gluing diagrams and blocked gluing diagram. So this is an example of a blocked gluing diagram. So it looks like a bit like the gluing diagrams we had before, except for one slight difference. In the diagram we had before, this was a 1 and this was a 2. So I kind of switched them. And we can see that if we imagine how we glue these diagrams to each other and try to construct the whole tree here, we will never get beyond 2, right? So every time we glue this diagram onto here, we will have a 2 here, and we will not change anything. And as we glue, it will always look something like we'll have a square, and we'll maybe have a bunch of stuff here, a bunch of stuff here, but we will have nothing here. So we will never reach anything that lies under here. So this is why we call it unblocked. We call it blocked, and this will be unblocked because even though we have this 2 that we don't expand, this 2, as we glue it onto something, becomes a 1, and then the 1 unblocks it. So as we've seen before, it kind of, you can see that everything, every path gets covered eventually. And this is, we can read this off in a very simple way from the gluing diagram. I just prefer to show the pictures here so we can get to the Higman-Thompson groups. So now if we have an let's say we have an unblocked gluing diagram, right? So then the whole tree is covered by those gluing diagram blocks, right? And let's say we have a path here and a path here that we want to show, are they, is the shift from the green path to the blue path, is it in our image, right? So what we can do is not bother with anything that's outside of the, this is too big. Not bother with anything this is too small. That's outside of the chunks where the blue and the green path end up, right? So because those are shifts, we don't have to kind of concern ourselves with anything that's above or next to it, right? So all we need to care about is those chunks here. So those chunks will be kind of the blocks of the gluing diagram, and the terminus here will be kind of internal vertices of the gluing diagram, which I will define short, or I will tell you what they are shortly. And we will have to see, can we shift this internal vertex to this internal vertex, right? And to kind of show this more explicitly, I will not be looking at our original gluing diagram because it's kind of a bit too trivial to show that it's surjective. So you kind of don't see what we have to do here. I will look at this gluing diagram. It's also relatively simple, but we have more internal vertices. So internal vertices here are just the white vertices, are the vertices which still have something lying underneath it, right? So we still have something that's covering it in our gluing diagram. So we have to check that we can shift between those three internal vertices. So to do this, we say first, can we shift from this vertex to this vertex? And then we will show that I think we can shift from this vertex to this vertex. So to see this, okay, what does it mean that we are able to shift? We want to shift without breaking those chunks. We want to always be like, for example, we map the green chunk to the red chunk, and we respect the numbering. Well, here we don't really, if we map just the green chunk to the red chunk, we won't get a shift taking 1 to 3 because we'll have this 2, which doesn't lie under 1, so it won't make sense. But we can glue again, right? We can do an iterated basis, which just means we will glue, for example, the gluing diagram again to the green chunk. And if we do this, right, this looks way better here, because if we want to go from 1 to 3, or from the between the two yellow vertices, we just map blue to red. So we map 1 to 1, 2 to 2, 3 to 3. And this is in the image of our gluing diagram. And it is the same as shifting between the orange vertices, right? So if we can kind of make an iterated basis that enables these shifts, then we say that it's then we can see that any shift between two paths that end up in those orange vertices can be R in our image, right? So the second thing we have to do to show that this gluing diagram is surjective is we have to shift this orange vertex to this. And again, here if we go again blue to red, it doesn't really work. But we can do another gluing, glue red, glue the whole gluing diagram to red, and we get something like this. And again, now if we glue the blue one to the purple one, we get our shift, right? And as those were our only those three vertices, and we see that we can go from this vertex to this vertex as well, because we can go to one to the previous one and back again, right? So because we've enabled all those shifts, it means that this gluing diagram must be surjective, right? So now we know, or at least we feel like we know, why when a gluing diagram describes an isomorphism. But the problem with gluing diagrams, they are great, but one problem with them is they don't describe uniquely our homomorphisms. So we can have two gluing diagrams that describe the same homomorphism of shifts. And I won't be showing exactly when they are when they define the same shift, but I can show one way of modifying them while not changing the underlying homomorphism. So it's called expanding, right? So let's say I want to expand this gluing diagram by 3. So what I do is I expand every 3 that I see here, right? I see that 3, I expand it. I see this 3, which I haven't pointed out. I expand it. And I see this 3, I expand it. And now I have a problem, right? I can't glue this whole gluing diagram to here because we have 3 vertices here and 4 vertices here, right? So we have to do something to change those roots. And what we do, we just get rid of this 3 and make those guys the new roots, right? So we get rid of them, make those guys the new roots, label them 3a and 3b, and voila, we have a new gluing diagram. And this new gluing diagram will represent the same shift isomorphism that the previous one did. All right, so now with 10 minutes to go, we can finally talk about Higman-Thompson groups and how we construct isomorphism between them. So Higman-Thompson groups will be the full groups of those pseudogroups of different of very specific graphs. There are many ways of defining Higman-Thompson groups. I will be doing it kind of in the vein of Scott. So I will define full groups to be simply the the subgroups of the pseudogroups of shift that are full, i.e. have a representative that goes from a basis to a basis. And in fact, I won't prove it, but it is in fact a group. If we take this graph and we take the full group of shifts of it, this will be the Higman-Thompson group. The graph will be referred to as GAN, as we have A and N. And our mission is, if we have N equal to M, and we have the GCDs of A and B being equal, then we want to define an isomorphism, and what we how we will describe our isomorphism, obviously, will be via a gluing diagram. So yeah, we will only show the right to left implication. The left to right implication was already shown by Higman, and it's not very relevant here. So we want gluing diagrams connecting GAN and GBN whenever the GCDs line up. And yeah, this will make sense, right? We will have an isomorphism between the shift pseudogroups, and because it's described by gluing diagrams, it will also be an isomorphism between the shift the full groups, i.e. the Higman-Thompson groups. I say I won't tell you exactly how those gluing diagrams that we will construct are actually surjective, but I hope it will be clear, or you will be able to prove it yourself. So first of all, we use Bézout's theorem, and we see, okay, if we have those GCDs are equal, we can find an L here such that it's L times A is equal to B modulo n minus 1. And we can also assume that the GCD of L with n minus 1 is equal to 1. This is very useful because every basis of GBN will have this amount for different K, this amount of paths, right? So the trivial basis will have one path, but any non-trivial basis will have B plus some K times n minus 1 amount of paths in a basis, because every time we add a caret to a basis, we are, well, adding n paths, but taking away one path, so we are adding n minus 1 paths. So this basis will be BR, so our the basis we associate with the root, and the partition CE gamma E will be arbitrary. So and the starting basis is trivial. So as an example, to make it a bit more clear and make sure we get through this, means let's say we have A equals 4, B equals 8, N equals 5. We see that 3 times 4 equals 1 times 5 minus 1 plus 8. I took 3 instead of 2 here because 3 is it has GCD 1 with 4. So we therefore have the following basis associated with R. So we have, we see that it's a basis of G85 with 12 leaves here, and we arbitrarily say, oh, this green goes to this one, this red goes to this one, and so on and so forth, and all the functions are arbitrary as well. So we don't really have to worry about it here. And now the difficult part is constructing BV, so the block associated to the internal vertex V. And constructing this BV is the same as constructing a floating gluing diagram connecting this Gn to itself, where the multiset associated with V is just L copies of V itself as well, right? So how do we construct this floating gluing diagram? Well, we will be calling Ln the pair of L and N reachable if there exists such a floating gluing diagram. And we will kind of show inductively that every Ln is reachable whenever the GCD of L and n-1 is equal to 1. So we will follow kind of a slow motion Euclid's algorithm where we don't take modulo, we just subtract. So we will show the lemma where we show that 1 and 2 is reachable, which is very easy to show. We will show that if L and N is reachable, then L plus n-1 and N is also reachable. This will be done by expanding the floating gluing diagram. And we will show that if L and N is reachable, we can add an L here. This will be done by a slightly more clever construction, which will add kind of L vertices here. So, and this way we can show that any Ln with the GCD is reachable by saying, oh, if L is bigger than n-1, we subtract, and we get, oh, it's reachable. So L minus n-1, n is reachable by induction. And we can use the second point to show that Ln is reachable. And if L is smaller than n-1, we subtract L from n. We say by induction and n minus L is reachable, and therefore Ln is as well by the third point. And if they are equal, then they must be 1 and 2. We assume n is bigger than 2. So the first point, very simple. We just take the trivial gluing diagram, and it's surjective. It's nice. The second point, we take some, let's say, floating gluing diagram. In this case, it will be 2 and 3. And L is equal 3, N is equal 2. And we want to show that L plus n-1, in this case 4, L is equal 4, and n is equal 2 is also reachable. And we just expand, right? As we did before, we expand in this case along the 1, but we can expand along any vertex we want here. So if we expand, we get this gluing diagram. And it's surjective as well if the previous one was surjective, because if we expand, we don't really change the function. It's not that simple, but it's almost that simple. Right, so this is pretty easy. And the last point, there we will have to kind of change the L, right? Change the N. We will have to add L to N, right? So let's take our previous diagram again. and we see, oh, we want to go from 2, n equals 2, to n equal n plus L. L is 3, so we want n equal 5, so we need to add 3 vertices, right? So we embed this gluing diagram into G5, right? And we see, well, first of all, this is not a basis, right? We've got a bunch of things here that can't be reached through it. It's not a basis. And second of all, we've got those 3 guys that can't be reached. And we can solve one problem with another problem, right? So we see, oh, to make it a basis, we'll have to add those 3 chunks right here. And those 3 chunks will make it into a basis. It's kind of the smallest amount of paths we have to add to make it into a basis. And well, we have added 3 chunks, and we need to cover 3 additional vertices. So every vertex gets 1 chunk. That's nice. And that's kind of the big trick here. That's kind of the moral reason why this isomorphism works, because it's not that not obvious that it should. Well, it's kind of the why the regular tree is so nice here, because we have 3 internal vertices here, and we have 3 roots here. And the fact that the amount of internal vertices and the amount of roots lines up, this is what makes the regular graph special. And this is what allows us for this isomorphism, right? So we add all those 3 chunks. So we first add blue, and we put them, we map blue to blue, we map orange to orange, and we map cyan to cyan. And now for the functions, well, we almost do arbitrary functions. The only thing we want to, we always want to have the functions only depend on this edge, right? So they have to line up here and here to make sure they are only dependent on the first edge they see, right? We shouldn't have like here 2, 1, 3. This wouldn't be a good function here. Right, so as I have -1 minutes left, I will just show you quickly how we construct the gluing diagram between those graphs, or those GANs, and therefore the homomorphism between Higman-Thompson groups. So first we've got the BR, so the B associated with the circles. That's very simple. And then we want the BVs, the bases associated with the squares, and we just do this thing again with expanding and adding. So we start with the trivial gluing diagram. We expand once. Well, we want 3 roots, right? So we got to expand again to get 3 roots. And then we want here 5 loops, so 5 edges. So we need to add. All right. And there we have the gluing diagrams, and give me any A and B with the same, and N with the same GCDs, and I will be able to construct this kind of gluing diagram as well. Thank you very much. Here are the 2 most important sources, i.e. Graham Higman's original paper and Enrique Pardo's paper, where with his original solution of the isomorphism problem. Are there any questions?
Okay. The Zoom reactions are floating up the screen. Yeah, any questions or comments? I suppose now that we've seen the talk, we could go back to Maury's question that he posed at the very beginning.
Yeah.
Maury asked, what did he ask? The complexity of what exactly? Of the isomorphism checking or of constructing the isomorphism?
Well, yeah, I mean, checking it is, it's just the GCD, but constructing it is the same. I'm assuming it's gonna be also polynomial because we just follow the Euclidean algorithm and do one construction after another. I think if I can hijack the question, the more interesting question about complexity, which I'm sure Murray would ask if he were here, is checking whether the gluing diagrams are surjective here. Because we glue something and then we see, oh, this enables the shift from 1 to 2, but we don't really know how far we have to glue to get this shift. And I'm not sure, but I'm assuming it can't be infinitely far. I'm assuming there must be an upper limit of how much we can glue until we can say, okay, this is hopeless, this is not surjective, but I'm not sure.
Okay. We'll pass that on to Murray.
Yeah.
Any other questions or comments? If not, let's thank Roman again. Thank you. And I will stop the recording.